So as we first start to work with an undisturbed sample retrieved from the field, these are the 5-inch diameter tubes that we use for manual sampling. We want to get access, of course, to the undisturbed material that's inside, but we also want to keep an eye out for material near the top of the sample that was probably disturbed by creating the borehole. And there's probably a little disturbed at the bottom just from shearing this specimen or the sample off at the bottom of the borehole. So we're looking for the good stuff in the middle. The sample's been stored in a high humidity room so that it wouldn't dry out, but it also has a bag over it to keep water from getting in, because free water getting access to the sample would relieve the capillary stresses and also result in more disturbance. So if we go to work with it, we're going to take the bag off, and we want to be sure that we push the soil out the same direction that it went into the tube. So this is the bottom where the cutting edge is. The tube was pushed down through the soil, right? So the soil was moving up through the tube, and we want to keep pushing it out the top. In order to do that, we want to push it as a solid piece, not get any shearing. So we want good one-dimensional push through there, and that means we want a nice flat surface across the bottom. This one's a little rugged, so we're going to flatten it out a little bit before we put in a stopper in there. This feels a little disturbed down here at the bottom. It doesn't need to be perfectly flat, but we do want enough space to be able to place our disc in there, which is going to act as a rigid spacer that pushes the soil out uniformly or one-dimensionally. And so we want this surface to be relatively flat. We know the very bottom is disturbed anyway. We're not worried about remolding this very bottom part a little bit. Oops. Okay. Sometimes the soil is all the way down to the very tip, and even in that case, even if it's flat, we want to dig in a little bit so that we can be sure that the disc that we're going to place in there is square against the bottom of the soil so that we can push it uniformly. Okay, now we're going to set it up in this hydraulic press. It's actually a UTM testing machine, but we're using just the hydraulics and the crossbars to help us push the soil out smoothly and uniformly. So we have our disc inside the tube at the bottom now. It's on a pedestal that is smaller, so we can push the tube down over that. At the top we have a collar that sits firmly on the top of the sampling tube itself, but has a hole that's as large as the inside of the tube, so the soil can come up freely. And then on top of that, we have to have some sort of a rigid hollow spacer so there's a place for the soil to be extruded into. Okay, and we're going to hold this straight, which the sample may not initially want to do, but once we start pushing, it'll grow to like it. And then we're going to lower this crossbar, start pushing the sample out. And we want to think about how much material we need for the test that we're going to run. But this is the first time we're taking soil out of this tube, and we know that that top zone is probably disturbed also. So we're just going to push out a little bit of soil, trim it, and see where we reach what we think is the undisturbed material. Holes here from the sampling head allow us to see what's going on. We're still in a void above the soil here now. Now we're getting to the top disc. That's what we were threaded into that provided the vacuum that helped us retrieve the sample. That's been in the whole time to help keep the sample at constant moisture. It has an O-ring seal right there. We need to extrude that out obviously also. There's the thread at the top. Okay. Go a little bit further and lift it up. this out, disassemble things here gently. And there's the top disc and the top soil surface. So we're just going to go ahead, rather than trying to remove the disc separately, we'll just trim that off with the first bit of soil. And we're going to use a thick, heavy-duty wire saw for that. So this is just a large diameter wire under tension, very straight. It's not sharp, it has no teeth, but it's plenty sharp for cutting bay mud. So the way you want to cut this soil coming out of the tube is to use the top surface of the tube as a guide. That'll give you a nice planar cut as long as you stay in contact with it on both sides. And we want to slice a little bit left to right as we go across the tube. And in the back, we can support the soil a little bit if we're worried about it breaking out. At the back, we can have a look at our soil at the cut. You can feel it. There's some organics here in the corner, and also it feels a little bit soft and spongy, spongier than it should for undisturbed bay mud at this depth. So we know we're still in that material that was disturbed by the auger before we push the sample tube in. And so we're going to want to extrude some more, slice off some more, until we find a good material to run our experiments on. Pushed out almost another inch now, and let's see if this material down at the bottom of that slice is less disturbed than that first cut we made. So again, I'm slicing left to right. I can actually feel from the resistance of the saw that this is less soft, less disturbed. This is promising. Okay. We're still not going to use this slice for anything because we know the top of it is disturbed, but we can have a look at the other side to see if what's below the cut is good. The way we're going to pick these soils up, we always want to keep bay mud in compression, because if we allow it to go into tension, it might come apart at a silt seam or something like that. So I'm going to wrap my hands around the side, squeeze a little, twist it, and then bring it down onto a disc. And actually, we want to look at the side on the bottom, so I'm just going to put it on my hand. And we have a much more coherent surface here. It's still a little bit soft. I have a couple of shells here, but it's much less spongy than the previous cut. And so I think we're into the material that we want to be testing. And so we'll reassemble the device, or the spacers that we want, and we'll look at the actual height of what we extrude based on the lines on here for which, how tall of a slice do we need? For a consolidation specimen, we need relatively thin slice. For UU triaxial or CU triaxial, we need a taller slice. And for something like a full-scale Shelby tube size specimen that we might use for velocity testing, or a larger specimen, maybe modulus degradation, we'd want probably as much soil as we could get out of this tube. And then, of course, we have to put the right amount of spacers in, because it's really crucial that we're not just watching the top. We have to make sure we don't push this sample tube down against the floor. That would be catastrophic for the sampling tube. It's pretty thin, thin-walled sampler. It would just crumple. All right, so we'll trim a large specimen today. So we've got another spacer now inside here. We've raised the crossbar back up, and so we have enough room to push almost to the top of here for a nice tall specimen. So we're gonna make sure we have this sort of manually straight again. Lower the crossbar. hydraulics in this system keep this head parallel to this base, which is what we want. Here comes the soil specimen. Across the top. Let's just check from back here, make sure everything's straight. So we would have stopped around here for a consolidation specimen, a 1D consolidation specimen. For shear wave velocity testing, we want a nice long travel path so that any small errors in that travel path have a small effect on the measured velocity. Close. Don't want to squeeze the sample, that would start disturbing it again, but we still have a little gap there, so we're good. Raise the crossbar, pull it on out. Off our guides. We're going to trim away the very outside surface of the material, no matter what experiment we're doing, so we're not too worried about accidentally touching that somewhere. And now we're going to trim across, get ourselves a nice parallel other edge. Our saw is tall enough that we can go right over the top. We can put our fingers on the back side where the saw is coming out, just to prevent the saw from breaking out a block. It's like when you're pruning a tree. And then again, we want to squeeze the sample, rotate it. Oh, it would help if I had a pair of hands here. There we go. Keeping it in compression. Let the weight keep it in compression. Here's our new fresh cut. Nice and firm. So our soil's ready to go. I'm going to put it on this lid here for now. We can take it into the lab, trim it to whatever specimen dimensions we want for the experiment that we're going to do. Want to make sure we seal up the remaining part of our soil because we may want to come back next week, run some more tests. We don't want to accidentally find that it dried out or got soaked with water in between, and then we'll take it off of here and put it into the base before we store it. To measure the laboratory shear wave velocity and also give us a specimen which we can measure the degradation of modulus and the damping values as a function of strain, we're going to trim a triaxial specimen of our undisturbed material, and we're going to place it in a triaxial cell with special caps that are fitted with bender elements. These are piezo ceramic wafers, sandwiches if you will, which have electrodes embedded in them and polarized ceramic such that when you apply a voltage, the benders want to curl. And if you disturb the bender element, when there's no electrical signal present, they actually generate a small voltage when they're bent or curled. So we're going to use them, they're embedded into the bottom cap and the top cap of this system. This is the diameter of Dames and Moore sample, and we want to make sure as long as those bender elements are aligned and parallel, we can measure the travel time that it takes for a disturbance at one end of the specimen to travel and reach the other end of the specimen and be detected. And you can use them essentially like accelerometers, or you can even transmit waveforms through bender elements with a voltage signal of your own choosing, a certain frequency or shape, square wave or a sinusoid. So we have an undisturbed specimen of the Young Bay mud from about 4.5 meters out in the field. We need to trim that into a nice Dames and Moore tube sample size. So that means we're going to have to cut it vertically in about half and trim it down on a soil lathe to give us the right shape for this experiment. So the Dames and Moore triaxial caps are about 61.3 millimeters in diameter. So that means we need slightly over half of the cross section of the material. So I'm going to cut this intentionally a little bit off center. We can save the other portion for another test if we want. Straight down, grab it from the bottom, separate two edges. I'm going to actually give myself a little assistance here with a spatula. This is mounted on there pretty good. I don't want to tip it because we could break the specimen in half. I'm going to get that spatula in there and pull from the bottom. There we go. Again, we don't need the whole sample, but do is transfer it to a glass plate, I think, here, and grabbing from the bottom, sliding it loose, there. We do want to use this other half of the specimen. We'll wrap that pretty shortly in saran, good sealed plastic bag. But this is the portion we want to work with. And the corners are going to stick out onto the trimmer too much. So we may as well take those off first. This is all good undisturbed material we could use for various things. They're kind of small for any laboratory undisturbed strength tests, but certainly would be good for Atterbergs or other characterization. And we're going to place this into the trimmer, which has guides that are set to make the trimming distance the right distance from the center line. And these caps are bigger than what we're going to need. You want to make sure we get all the faces close enough, though, so that we're trimming something away from every surface. A little more this way. And then we're going to trim it just like we trim the UU samples or the CU samples. We're going to use the wire saw, the fine wire saw, and then the blade, the rigid blade, to give us that nice cylindrical shape. And of course, during the process, we'll be sure to get some material for water content, because we're going to want to know, we'll be able to measure the moist mass easily, but we want to know both the water content and the dry mass, dry density, for characterizing the material. So we finished trimming the specimen with the first the wire saw and then the blade, giving us a nice cylindrical sample of the right size. And we're going to put that aside for a moment. And we want to set up the cell. I'll put the water content trimmings in the oven. I already got my moist mass, so we'll go to dry mass. I'm going to move the cell over. I've already measured a reference height using a cylinder that's 105.0 millimeters tall in place of the specimen, and I put it under a dial gauge. So I have a precise measurement to hundredths of a millimeter what the height of this system is when I have this known reference in there. So after we have our specimen in, we can measure it again in the dial gauge and get a nice precise height. But for right now, we need to take this apart a little bit, and for that I need an Allen wrench so I can move this up out of the way. And in fact, I guess I should take the cap all the way off, because it's hard to see what's going on in there. So this just screws in. Be a little bit careful with the bender elements. You don't want to sit them down on that surface or bump them too hard. So we have a relatively large bay mud specimen, and one of the things we want to make sure is that we have drainage, accelerate the drainage, so we're not dealing with such a tall drainage height for consolidation and getting to a new stress, changing stresses. So what we're going to do is we're going to add sort of a simpler version of the bishop's pajamas that we had earlier in the CU testing. We're going to have vertical paper strips, but not a continuous ratio of a half. We're just going to put 3 filter strips around the edge of the specimen, and those are going to have to connect with these tabs on some filter paper that's on this disc. We have a little window there so the bender sticks through, and we'll position the soil on top. Then we'll put the filter strips where they need to be, and then we'll put the membrane on after that. That's how we'll get this set up. So let me go cut those filter strips. We're going to position the specimen directly over the cap with the filter disc in place, the one with the tabs around it. And we're fortunate with Bay Mud, and it's also important we got the moist mass of our specimen before we set this all up, otherwise it's kind of a missed opportunity. The young Bay Mud is so soft that we don't need to make an excavation. We don't need to make a space for the bender element to occupy. It'll just shear around it and have a nice tight fit there. That's especially true as long as we can get it in the right place on the first shot and not need to move it around. With stiffer materials, sometimes you need to actually carve a slot so the bender element can fit into a stiffer or more brittle material. So let's place this over the specimen. And it doesn't have to be perfectly centered, but we'd like it to be close. So we're feeling where it is relative to the front and back and side to side, and then we're just going to lower the specimen straight down on there. And the Bay Mud, especially when it has confinement on it, will pull in tightly around the element. That looks good. So we're ready then to put the membrane on, and to do that, and the filter paper drains, we're only going to use the bottom drain line on the device. So we're only going to have this connection with the filter paper at the bottom. The top cap is going to be undrained, so we don't need to worry about how the filter strips work up there. But we are going to have to sort out how to put the membrane on, and instead of unrolling it, we're going to use something called a membrane expander, which is a hollow cylinder. The membrane is smaller than the cylinder, but by applying vacuum to the inside, just like we did with the plain strain sand specimens and the vacuum sand specimens, we're going to pull that membrane out against the expander, and that'll allow us to slip it over the sample, and then we'll be able to take the vacuum off, and the membrane will squeeze in around the specimen afterwards. It takes a little bit because there's some filter paper in there. Give us a good fit. There we go. And so the trick is to have these strips of filter paper in the right position. And the right position is, of course, defined by touching these tabs at the bottom and then coming up toward the top. As we take off the vacuum. Well, while I was setting it up, I got all 3 positioned in the right place, and I put the membrane on so that they're touching the tabs here. And so we have a connection between filter paper strips on the sides and the filter paper tabs that connect to the bottom drain line. So that was a little trickier than I sometimes experience, but it worked out okay. So now we need to, of course, cut those filter strips far enough up that we can get the O-ring seals below them, because we don't want to have the filter paper going right past the O-ring seal. So we'll do that, and we'll have to do the same at the top. The membrane is also a little extra long, so we'll just be rolling some of that up out of the way. And then we can put the top cap down into position. So we have the membrane on, the filter strips are in place, but we haven't put the top cap on yet. And before we do that, we probably want to get everything aligned using the top of the cell. And we're going to run this test with vacuum confinement. We're going to apply vacuum to the inside of the specimen so that these we can access the sample, we can measure the diameter and the changes with stress and things like that. So we want to get the cap in, but we don't have to worry about the seals of the red wires. Those are the electrical leads which carry the voltages that we're going to measure with the oscilloscope once we're ready to measure velocities. So I've got the cap threaded into the rod, and I want to make sure that the fender element is oriented properly so that it's parallel with the one at the bottom. If you don't do that, then you get some funny answers. Okay, you want to have everything centered, and then we're just going to push the top cap in just like we put the sample into the bottom. And then we can roll up the membrane and seal it with an O-ring also, and we should be good to go. So to actually provide the confining stress, again, we're going to put a vacuum on the pore pressure, or the pore water. We're going to do that through a vacuum chamber, as we've done before. We're not going to be subsequently trying to back pressure saturate it, so it's not really a matter of removing all the air, but it's a way to establish the pressure that we want, or the effective stress that we want, by putting that vacuum on the inside of the specimen. So I've connected it to the vacuum source. For now, I just want to bring it up to perhaps half an atmosphere. We're working through just the bottom drain line. The top drain line is not connected, right? We're not going to use that today. But as we apply it, we'll probably see some air come out, and we'll see a change in the membrane as we pull that air out from between the soil and the membrane itself. Shouldn't be a whole lot. We kept the stones dry. The pore stone at the bottom is dry. Okay. And what was the effective stress before we opened the valve? Well, we don't really know, right? It was an undisturbed sample with negative pore pressures already. So depending on the depth that it came from and the depth below the water table, right? And the degree of disturbance, how much of that effective stress in situ that we captured and kept while it was undisturbed here in the lab, we might not really be changing the effective stress very much. This is more a way to know what the effective stress is as we run the tests. So it shouldn't need to consolidate a whole lot. But now that that effective stress is on, we'll give it a little bit of time to equilibrate, and then we can measure the diameter of the specimen and also the height again by putting the system back under the dial gauge to see what the dimensions are. The nice part about working through the height measurements through the top of the rod is even if we had a closed chamber, we could keep monitoring the specimen height by looking at the position of that rod on the dial gauge. Once it's equilibrated, we'll be ready to connect the red leads, the electrical leads from the two bender caps, to our oscilloscope back here, patiently waiting, and we'll be able to look at the travel times from the bottom cap to the top cap. So our specimen is set up. We have half an atmosphere of confining stress on it, and the lead from the bottom bender element cap is coming in here to channel 1 on the oscilloscope. The lead from the top cap is coming in here to channel 2. So this is a digital oscilloscope that can record both of those channels at the same time. We're going to have it trigger by seeing a waveform at the bottom cap, and then it'll hold that waveform until we either erase it or there's some noise. And since it's digital, we can actually pan through each of the channels and take readings, time readings, of where specific peaks are. And that's how we're going to look at the travel time between them. The yellow line here is just a ground that keeps a nice stable 0 voltage for us relative to the ambient situation around us. So let's see what happens. I'm going to create a disturbance. Instead of by sending an electrical signal to the bender, I'm just going to use them as accelerometers. I'm just going to tap on the bottom cap, and almost instantaneously, of course, we'll see that disturbance in the bender that's embedded in the bottom cap, but then it'll take some time to travel up to the top cap. So let's see how that works. Not hard enough. There we go. So what we see in this travel time, and I've done that about a half a dozen times to make sure that it would work, and the waveform is very similar each time. So what we're going to do then is move around the cursor, essentially, or move the traces around until we can get comparative readings for a characteristic point. And for this trace, I'm going to suggest we start by looking at the trough, the low point, which is very distinctive in both of these records. And to do that, I need to move around the horizontal position of the time. So the traces are just moving around, and I'm moving the channel 1 value to be right on one of the guidelines. And I have a position of 2.200 milliseconds. So 2.2 milliseconds. And if I line up the other trace with the same guideline, I have 4.16 milliseconds. So my travel time is the difference between those. If I use some other point, I would have 2 different values, but the difference between them would remain the same. So that's 4.1 milliseconds minus 2.20 milliseconds. And that's the travel time it's taking for this disturbance to travel the length of the specimen between the bender elements. And we typically assume that the tip of the element is the active point. So it's really the distance. We want to get the velocity, we want to look at the distance tip to tip between the elements themselves, which is of course a little bit shorter than the height of the specimen, because each element is sticking into the specimen about 5 millimeters. So we'll get these dimensions all measured and documented and sent to you. And now that should give us a value for V sub s, the shear wave velocity, at this confining stress. And so we're going to leave it at this confining stress and then run cyclic triaxial tests. And that will show us how the modulus, the shear modulus, G, we can calculate G max from this value of V sub s and the moist density. But we can look at how V degrades or declines with shear strain level in a triaxial test as well. So we have our specimen now fully trimmed. It's been under vacuum for most of a day, 1/2 atmosphere at this point. And we brought the cell over here. Again, we're not going to use the triaxial chamber. Instead, we're going to just rely on the vacuum confinement as our sigma 3 prime. It's isotropic, of course. We've modified the triaxial system to make it more useful for what we're doing today, which is small loads on a soft specimen to try and get small strains. So one of the nice features of this system is that it's very modular. And so we swapped out a larger piston for one that's half the size or quarter the area. So we have better control for given pressures from the device. We get much smaller changes in load, so we have better control there. And we've changed the load cell to something that's about 4 times more sensitive. And we've changed the LVDT to be twice as sensitive. So we're switching in components that are better for what we're doing today, even though this specimen is bigger than our compacted strength test specimens, we're interested in very small strains, and so we need that fine control. Otherwise, the system is pretty much the same. The load cell and the LVDT feed into the signal conditioner. We're not really going to use the volume change device or the effective pressure transducers at all. We're just going to note what the vacuum confinement is separately. So those are the only two channels, the LVDT and the load, that we're really going to worry about. And we'll set this up with all the input data from the specimen so that what we get out are deviatoric stresses and axial strains directly. So after we set up the initial home menu, put in all the specimen dimensions and equipment dimensions, we turn on the pressure to the system and set all the pressures that it requests, some of which aren't going to affect our test at all, but it's menu driven. You have to move through the menus appropriately. We get this main choice of tests to run again, and we're going to choose the dynamic test, which is the open loop cyclic test. So it can run at a frequency of 1 or 2 hertz, or a little slower if you want. We'll probably run a little bit slower. And when we say open loop, that means the computer is going to decide ahead of time what pressures it needs to send at that frequency of loading, and just apply them without double checking to see if the load in the load cell is what it's expecting to get or not. Open loop loading like that provides much more uniform, smooth loading, but it might not be exactly on the target that you're asking for. But in our case, we're interested in developing a curve of the modulus with strain. And so if the strain from a given data point is a little higher or a little lower because the stresses are a little higher or a little lower than we asked for, that's fine with us. So we prefer to have nice interpretable data. So I'm going to click Dynamic Test, and we have some choices. We're going to choose a sinusoidal waveform instead of a triangle. You can also create your own user waveforms. I've not tried that, but we're going to put in a relatively small peak-to-peak deviator load. So this whole area is the deviator stress. So let's put in a value of 10 kilopascals. Start with compression. You have the option in this, if you have a chamber, to also cycle the confining stress, especially if you go slowly enough. And so it will adjust the chamber pressure within the specimen at the same frequency as the deviator stress if you want to try to keep a constant mean stress while you're running the cyclic deviator loading. But we're not going to mess with that, so we'll leave the amplitude at 0. And in that case, it doesn't matter if we start with compression or extension. And we're going to run at a period of 2 seconds. So that's half of hertz. And we're going to run 5 cycles. At very small loads like this, it probably doesn't matter how many cycles we ran. But when we get out to larger loads and larger strains, the more cycles we do, the more pore pressure we're going to generate, and the less our subsequent tests are going to be at that same effective stress, unless we want to wait hours between tests to let all those pore pressures dissipate. So we're going to look at just a couple of cycles. Usually, we'll start out with, let's start with 4 actually instead of 5. And we're going to call it an undrained test. Doesn't really matter. The specimen itself is drained, of course, because we have a vacuum chamber connected to it, and if water wanted to flow out, it could. All right, so we're going to proceed from there. We have to tell it what the maximum strains might be. When should it stop the test as sort of a backup? Things go out of control. And 10% is way beyond what we might get. We're going to say 1. I don't even expect to get to that. and we would like 50 points per cycle, not 10 or 25. This is one of the things I wish you could just type in instead of having 3 choices, because sometimes you want even more than 50 per cycle, but that's okay. The next, we have to close drainage valve A. You can do that. And now we have this option where the system will let us test the system and see if we'll really get the amplitudes we want. Again, we don't care too much about that, so we're going to just go ahead. We're not going to do the calibration part, and we'll go ahead and start. And there's no point watching the specimen because you can't see 0.02% strain happening. So we'll keep an eye on the graphs on the screen. Okay, so what did we see? Well, the deviator stress with time cycled pretty nicely. The load cell picked it up pretty well. Was it plus and minus 10? Sorry, not plus and minus 10. Was it 10 peak-to-peak amplitude? Well, I'd say about 3.5 and 2, so more like 5.5. It undershot what we were asking for. That's okay. The lateral stress was supposed to stay constant. It basically did. No excess port pressures were measured because it's not connected. And unfortunately, because the smallest axial strain you can put in here is 1%, we can't see very well extremely small strains happening here. So there may be something going on at small strains. It should be, again, at the same rate as what's happening here, but not a whole lot of strain for sure. So that was a small strain. In fact, it was even smaller than we asked for. So we'll go ahead and run a second one at a larger amplitude and see what we get. So we've gone through this menu again, and we've asked for 16 kilopascals peak to peak instead of 10. So let's see what we get. And I'm going to watch the voltage output of the LVDT itself and see if we get a cyclic response. Oh, definitely. Definitely about plus and minus 50 thousandths of a volt. So, and very clear signal there in the measured response too. So, to develop a suite of modulus degradation as a function of strain, we'd want to run a series of this test with gradually increasing strain amplitude, and then plotting the modulus for each of those tests as its own data point, right? Because from this we can get a hysteresis loop of the shear stress and the shear strain, and it won't be all exactly the same, but we'll get one data point, we'll pick one good hysteresis loop from a given test and figure out what strain that's at, see what the modulus is, see what the damping is, and then we'll combine a suite of those tests at different strain amplitudes to develop the degradation of the modulus with strain and look at the area within the hysteresis loop to get the damping. All right, so I'll run the rest of the suite and we'll process it in our lab groups.